Okay, let's take a look at the energetics and the biochemistry of hydrogen oxidation. So let's just kind of start off drawing a little bit of the cell here. So let's just make some membranes, these wavy lines are membranes, and this is going to be one of the hydrogenases that's going to be used. And then a little bit later we'll need an ATPase molecule. So there are a couple of molecules there in the cell membrane. Okay, so this is a hydrogenase, and that's going to take hydrogen and split it into protons, which result in acidification of the environment, and electrons, and they're going to be used to generate a proton motive force. So let's start with some hydrogen gas here outside of the cell, and think about the electron movement. So the hydrogenase will take some electrons from the hydrogen, and obviously it's going to liberate some protons, and that'll contribute to acidification. And so these electrons will be passed through a series of cytochromes in small proteins in the membrane. And it doesn't matter what the names of those are, but just like in a mitochondrial electron transport chain, as the electrons move from more electropositive to more electronegative, protons can be pumped to generate a proton gradient. So the protons coming from inside the cytoplasm in here, and then being moved across the membrane as electrons move through the electron transport chain. And eventually then the electrons come out of the chain, and in the case of this bacteria, we're going to use those electrons to reduce some oxygen to produce water. And so we've built this proton motive force, and that can be used by an ATPase to power oxidative phosphorylation. So we'll take ADP and inorganic phosphate and use the power that comes from the proton motive force moving down its electrochemical gradient to generate ATP. So that's how we're going to make ATP using this system. But this bacteria, in this case we're looking at Ralstonia eutropha. This is an example from your textbook. In this example, we've got autotrophy to deal with. So that means we need to make some NADH. So I'll just put the NADH down here in the cytoplasm for now. So we've got to make that NADH. And because hydrogen has such a positive standard reduction potential, and it's higher than NAD plus's standard reduction potential, we can take electrons directly from hydrogen and give them to NAD plus to make NADH. So how does that work? So for that, we're going to just allow the hydrogen to diffuse into the cell, and that can be bound by a second hydrogenase, the cytoplasmic hydrogenase. I'll just call that one hydrogenase again. And that enzyme is able to take electrons from hydrogen gas and is able to use them to reduce NAD plus to NADH. And so that gives us the NADH that we can use then to convert carbon dioxide, and we're going to use some ATP, and we're going to convert the carbon dioxide into cell material. So we're going to use it to do cell biosynthesis. So the only reason this works is that is because the hydrogen's standard reduction potential is so much more positive than that of NAD+. So there's no need for reverse electron flow here. We've got a nice simple system in which we can make ATP and we can make reductant for autotrophy.